Alright, we'll get started and let everybody else catch up. It's a great pleasure to have Amir and Tajdini, visiting us from Cornell. Who's going to tell us all exciting new work related to the resolution of the black hole information paradox.
Thanks, William. Thanks for the invitation. It's a pleasure to be here. So today I'm going to tell you about Replica wormholes and the information paradox. This is work mainly based on this paper and by TAMU and follow-up work. And this work was done in collaboration with a group of people, Amir, advisor Tom Hartman, Cornell and Russia William. Okay, so why the black hole information paradox is actually a problem? In its most famous form, you can imagine you start from a collapse of a pure matter. It collapses, it forms a black hole, and as the black hole forms, it starts to evaporate via Hawking radiation. And Hawking calculated the density matrix and the entropy of the final radiation, and it doesn't match with the initial entropy that you can calculate. It's pure, it has to be zero, but you will get some entropy for the radiation. In more details, if you look at the evolution of entropy of black hole versus time, as the black hole evaporates, the thermodynamic entropy of black hole starts to decline, goes to zero, whereas the entropy of radiation, it just grows until this time that the black hole completely evaporates. And after this time that they become equal, we have a problem with quantum mechanics, because if you imagine any of these times, you have some radiation which has this much entropy, but the black hole entropy, which is a coarse-grained entropy, is not enough to purify your radiation. So there's just not enough entropy available in black hole to make the whole system, black hole plus radiation, pure. So this is called phase transition, and if we plot the radiation for the actual system, like a usual system, like a piece of coal, we expect to find this behavior. We expect to find that as the radiation comes out of a piece of coal, initially it starts to increase because it's entangled with the stuff inside the coal, but as everything inside the coal is starting to come out, we expect the entropy, radiation entropy, to goes down back to zero. And note that this discrepancy between what quantum mechanics predict and what you actually calculate, it's a big discrepancy. It's an order 1/g Newton discrepancy of order black hole entropy. So the main question is, what is wrong with Hawking's calculation of the entropy? So that's what we are looking after. We want to know how this discrepancy happened. We think that Hawking's calculation was under control. It was a semi-classical calculation. So we would like to know what has been done wrong in this calculation. So in this talk, I will show you that by constructing a new saddle point in the gravitational path integral, we can actually get a unitary page curve. So this curve that I showed here, like piece of coal, or the curve that you expect from quantum mechanics for a unitary system, that's called page curve. So I will show how you can get a unitary page curve by this new saddle point. I should say that this resolution will be independent of holography. I'm going to use holography in the intermediate steps as like guiding us, but like I'm not going to use the details of holography in this derivation. And I should emphasize that there's a lot more to information paradox just to get page curve, because we really want to understand at the end, if you throw something inside the black hole, how that thing will be encoded in a late-time radiation. And I don't have anything to say about that one. So that one I'll call microscopic information paradox. I will be just talking about page curve, which is one diagnosis of information paradox. So my plan is I will first tell you a different version of information paradox. This is a paradox for ADS black holes when you glue it to the flat space. And then I will tell you about the proposals for getting a unitary Page curve, which is known as the island rule. And finally, I will tell you about the derivation of this proposal to get the unitary answer, which I call Replica wormholes, and we get there. So please stop me at any time, questions, so we can discuss. And so let's go to the first one. Okay, so information paradox in ADS has some differences with the information paradox in flat space. So the difference comes from the fact that thermodynamics of black holes in ADS is different than flat space. You have, for example, large black holes in ADS that they don't evaporate. The reason being that basically this Hawking radiation will get to the boundary in finite time and fall back into the black holes. So it's stable, it doesn't evaporate. And usually in the context of ADS, the information paradox is encoded in exponentially decay of correlation function in ADS. So this is the famous Malvicena eternal black hole version of information paradox. And the important lesson here is that you don't have a large discrepancy like flat space, but still there's a problem, and that problem is hidden in exponential tails of correlation functions. So if you calculated the 2-point function for some local operator in the black hole geometry in ADS, you will find that they indefinitely decay exponentially, whereas on general grounds, for a system with finite entropy, you don't expect the correlations to go to 0 forever. So you expect that there will be non-perturbative effects, and they cannot completely disappear correlations between your operators if the system has finite entropy. But because it was hidden in this exponential effects, exponentially small effects, it wasn't easy to analyze this problem in the context of ABS-CFT. Of course, there's a lot of literature about understanding how the 2-point function in black hole background will behave from the point of view of CFT, but ultimately, information paradox is the question about effective field theory of the bulk. So if we say that we solve it or we try to solve it, we need to understand it from the bulk perspective, not just from the CFT perspective. So very recently, there was this model proposed by this group of people. The paper came basically last spring by Jeff Pennington and Amir, Engelhard, Maroff, and Maxfield. They proposed a new model. So they considered ADS black hole, but they glued the ADS black hole to some flat space region. And they set the gravity to 0 in those flat space region by their hands. Like that's just a part of their model. So there's no gravity in these two regions. The gravity only is in this green region. But they consider some matter field which exists in both flat space and ADS, and you just impose some transparent boundary conditions for the matter field at the interface. So the matter can go from flat space to ADS and vice versa. And the good thing about their model was now the radiations that previously falls back inside the black hole, now it can actually escape to the flat space. So now you can actually get a large discrepancy between the quantum mechanics prediction versus the semi-classical calculation. So now it becomes more like flat space, but at the same time, because they consider black holes in ADS, you can also use all of the technologies developed for ADS-CFT to analyze this problem. Things like entanglement, wedge, reconstruction, all of these Yutakenagi formula that we get into them very soon. But this was a new model, and I'm going to focus on this model. I should say that most of these calculations I'm going to explain, they're in context of 2D gravity, 2D JT gravity, plus some conformal matter. But for some of the discussions, it can also, I'm not going to use 2-dimensional gravity explicitly.
Yes.
Yeah.
I'm assuming that, so along that long interface, I imagine that the curvature is also continuous, and it dies off to 0 at that interface.
That's a good question. So So what we impose is we impose that the metric itself be continuous at the interface, but because the curvature in AES side will be different than curvature on the flat space-time, there will be a jump in the extrinsic curvature on two sides.
Oh, I see.
But that jump will be only at the boundary. So there will be some contribution, but it's just contained at the boundary. Okay, so I'm going to explain a version of information paradox in this setup. So the black hole I was considering in the previous slide was an eternal black hole, actually. And just like the eternal black holes in flat space, there's an ingoing flux and outgoing flux, and you just tune them such that they will be equal. So the mass of the black hole will be the same. And schematically, you can think about the matter contribution here as basically these Hawking pairs that I draw here. So there will be right-moving Hawking pairs and left-moving. And as I said, this is a two-dimensional gravity setup, so there won't be any gray body factors and scattering. So just right-moving ones will move without back scattering from left-moving one in the setup. Yes?
So why should the amount of matter coming inside be equal to the entropy outside? So why?
It doesn't have to be. That's kind of like part of the boundary condition I'm choosing. Like you can have the situation that you will say, oh, I'm going to turn off these fluxes here, and then the geometry won't be just this. It will be evaporating.
So you said on the left, the right region, the gravity is 0.
Yes.
So why is the matter displayed inside?
Well, so the matter, we have some quantum fields, and quantum fields exist everywhere.
Okay.
So that's part of the model. That like, oh, thanks.
What was R?
Okay, yeah, I haven't talked about R. So now I'm gonna try to calculate the entropy for this region R. R is a half line on the right side, union half line on the left side. So that's my region, and the goal is to calculate the entropy of this region. And we want to calculate that as a function of time. So you have two half lines, you just evolve both of them in time, and you just ask what is the entropy for this region R in this eternal black hole. So as you can see from this picture, as this region R goes in time, like evolves in time, there are more Hawking pairs. So this one on the right will absorb the one on the right side. So there's another pair which falls inside the black hole. So this is the horizon, one horizon, this is another horizon. So one partner falls inside the horizon, but the one which is outside the horizon will be captured by the one on the right. And for left-moving ones, similarly, the one on the left will capture one of these pairs of the Hawking radiation which moves toward the left. So with this picture, we expect that the entropy as a function of time for this region R should just grow, because more and more these Hawking radiations will be absorbed by this region R. So if you calculate the Hawking entropy, it just increases forever. However, similar to the flat space, there's a problem, because the black hole entropy is finite. So if you think about these slices, that you have some R and you have some slices inside black hole and you have R, if these slices are supposed to be pure on the full slice, the black hole entropy should be able to purify the radiation. So there's a finite coarse-grained entropy or thermodynamic entropy available to black hole. And if the whole system of radiation plus black hole is going to be pure, the Hawking radiation cannot indefinitely grow. In fact, here, because you have two-sided black holes, one can show that the Hawking radiation cannot be bigger than 2 times the black hole entropy. Whenever this happens, similar to the flat case that I showed you, there's just not enough entropy in black hole to purify the system. And from that time, you're in trouble with quantum mechanics. So if from the quantum mechanics perspective, you expect that it increases, but at some time it should saturate. So that's basically the paradox in this context. and it was basically addressed in the paper by Amir and a paper that I was part of it. So we considered this version of information paradox because it was easier. Like, we are interested also in about evaporating black holes, but this one, because the black hole, it doesn't evaporate, the geometry is the same, we just considered some funny looking time slices like this. So we just evolved the R in both sides similarly in time. We get this information paradox, but the geometry is the same throughout.
Is the geometry for your slicing chosen so that you capture all of the pairs? Or what's the, I don't understand, what is the logic for this, for choosing R in the way that you did and then evolving that?
So the logic is if you choose the slices this way, then you see that the entropy will grow. I mean, this problem has a boost symmetry, so if time goes forward in this direction, there is a time slicing in which time will go backward in the other direction. If you consider those time slices, then the entropy will be the same. But if you choose this time slicing that you break the boost symmetry, you time evolve on both sides similarly, then you will see that you capture more and more these Hawking pairs and you have this problem. Okay, so now I'm going to go to the proposal for getting this page curve for this example, which is known as island rule. But before getting there, let me just mention that the very important ingredient in the whole story is played by this notion of quantum Yutakenagi formula. A lot of you may have heard about the Yutakenagi formula. It's just a trick for calculating the entropy of regions in the boundary by minimizing the areas in the bulk. So later on, this formula was generalized by Engelhard and Wall by considering also the matter contribution in this formula. So in usual RT's formula, we just consider area of these surfaces. So here, for example, it's a two-dimensional Penrose diagram. So I suppress, you can imagine I suppress the transverse direction. So this surface Q that we want to calculate this area, we usually just find the Q by minimizing the area of this point. But this proposal is that we also need to consider the matter contribution from the Q to the boundary of ADS that we are trying to calculate its entropy. So this is like a correction to the Yutakenagi formula, and for most purposes, this second term is not as important for the first term, because first term it comes with 1/G Newton, it's big, but if it happens for some kinematical reason that the first term will become small or the second term will grow, then these two can compete with each other. Otherwise, in most cases, we just need the classical piece, which is area over 4G. Yeah.
So are you extremizing for all possible Q?
Yeah, so you have to choose a time slice. For example, in a static case, you just look for what Q will extremize this quantity. And once you find the Q, you can plug it back in, and that will give you this is also called generalized entropy for that subregion.
But I mean, like, is B just some location on the areas?
Right, so here I consider that I'm trying to calculate the entropy for the full boundary ADS.
Yeah.
So typically this formula is useful when you consider subregions in the ADS boundary, but because here is a two-dimensional model, there is no subsystem here, so subsystem is basically the whole point. The system is a point. If it's two-dimensional, this will be one-dimensional, and if you try to calculate entropy of the boundary ADS using this quantum RT formula, this is the prescription. You just consider some point Q, which is unknown, and you just determine it by extremizing both the classical piece, which is area over 4G, and the matter between Q and the right boundary. So that's basically the prescription.
Why does Q determine B?
No, Q, so you choose this point at this time, and then you pick a Cauchy slice, for example, and then you will be looking for a point Q so that it minimizes both combinations between them. And we say that
B is the data.
yeah. And Right. And once you have this entangling surface, you can also find its domain of dependence, and that's called entanglement wedge. And it's important because in ASCFT, we think that if there's some region in the bulk, which is inside the entanglement wedge of a region in the boundary, those operators can be constructed purely from the operators in that boundary. So now I'm going to tell you the proposal. So remember that we had this problem that entanglement entropy for this region R grows indefinitely as a function of time. So now the proposal is that the entanglement wedge of this region R contains a region behind the horizon. And we'll try to unpack this sentence. So the idea is very bizarre. So you try originally to calculate the entanglement entropy of this region R in flat space. And we saw that by considering just the matter contribution hitting this region, it increases indefinitely. Their proposal is we should assume somehow this region R knows about the stuff behind the horizon, knows about the operators and things behind the horizon. So for example, in usual ASCFT, we say that if you just restrict yourself to the boundary region knows about the region inside the bulk. So it's like extension of the usual ASCFT to like this flat space region. So we are saying that the flat space region that you try to calculate as an entropy is actually knows about the stuff inside the bulk. It's even more stronger than that, because if this region, which they call the island, is completely contained in the entanglement wedge of this region R, it means that any operator in the bulk in principle should be constructed from the operators only in this region R. So somehow they're saying that there's this region appearing and the region R is entangled with that region, which is behind the horizon. So I will try to explain this better as we go through the derivation, but just for a second, if you buy this, then it's not hard to see at least why we don't have an immediate paradox. Because now this region I will capture the other pair of this Hawking radiation, which was falling behind the horizon, similarly for this one. So now when you consider the matter contribution on R union this island, this blue one and the green one, they don't contribute to entropy anymore. So the entropy of the matter in this situation, it can be finite. But as I said, I will try to explain this more.
It's not a problem that like, there aren't observers who can actually combine all of this data. You can actually see all of these regions are there.
Well, their proposal is that if you consider the rest of this region in the flat space plus the boundary of ADS, they will have access, for example, to this region. So they're designed is such that if you consider the whole system, like the boundary of ADS plus this smallest part here, and this two radiation, the whole system will be pure. And we will see it shortly, but remember that if you calculate just, for example, this was actually not just an example, but if you really calculate in this case the matter plus the area, this point won't actually see the whole thing in the geometry. So from just point of view of right boundary, you will have access to some finite space. So basically the question is, who is claiming the rest of this space? So right boundary doesn't see it, left boundary doesn't see it. So they propose that this region R, in a full quantum gravity partition function, the information about this region behind the horizon is somehow encoded in this region R. In terms of formula, they propose this formula. So basically, they consider that this region I is part of the entanglement wedge of region R, and they just applied the generalized entropy that I showed you to this region R union I. So they consider this quantity, the area of the endpoints of this island, plus the matter contribution R union I, this island. And then you go and extremize this quantity to find where this island should appear. So the goal is to find this point P1 and P3 by this extremization procedure. And once you extremize this, you will find some answer. And if that answer happened to be smaller then the answer that you don't have any island, so you just consider the matter contribution on region R. Their proposal is you have to choose that one as a true entropy of this region R. So you assume that you have no island in this formula, you have one island, you have multiple islands, you go and extremize over all possibilities, and you will always find them, you will always pick the minimum one for the entropy. And originally they proposed this by holographic considerations. The matter field that they considered was a holographic CFD, and they put the whole system as a brane into some three-dimensional gravity. So the original intuition behind this proposal was from Yutakenagi formula in that third-dimensional gravity. But our goal was kind of simple-minded. We just wanted to understand this bizarre island rule from the first principle calculation. Like you have gravity path integral and replica trick, how this island rule can emerge as a prescription for computing this entropy of R. Which brings me to the third part of the talk.
So I had a
Yeah.
question for the previous slide.
Sure.
So why are you not extending the blue line all the way to the boundary?
So in their proposal, the endpoint of I is not up to you. So you just choose the endpoints of region R because that question should be meaningful. You know, it's flat space, so region is meaningful. It's not like that you have gravity, so you have to care how do you define regions, and gauge invariance, and all of that. So you choose your region, but the endpoints of island will be chosen dynamically by this formula. So you don't have control over that. So if it happened in one case that as you move this point, this quantity will become even smaller, that's the correct choice. But it turned out here it will be some, for a finite region R, there will be also some finite island. So it won't be like going all the way to the boundary. So I'm going to go to derivation of this, and the derivation, we tried to also derive this, and also there was another paper by Stanford group that the model was slightly different, but they reached the same conclusion. And our goal is to calculate this entanglement entropy for region R, the one that from one hand we have problem, from the other hand island rule seems to make the problem okay. And if you try to calculate entanglement entropy in Lorentzian signature, it will be hard. Like any other thing in quantum field theory and gravity that is hard in Lorentzian signature. So we use this ancient trick of going first to Euclidean signature, do all of the calculation in Euclidean signature, and just at the final step, analytically continue the answer from Euclidean to Lorentzian. So we don't do the calculation directly in Lorentzian. Remember, the goal is to find trace row log rho for the region R. So the way we do it is we do it with path integral. So this was the geometry I showed it to you. It's half of it, and we would like to know what's the state. So there's a state that if you have that state, you can evolve it in time, and you will get the state in other times for this geometry. And we do this by doing the path integral in Euclidean direction. So this was the Lorentzian direction. This is Euclidean direction, and the idea is doing a path integral on this sheet is producing for you the state that you're trying to calculate. And once you have the state on this time slice, you can evolve it in any direction you want.
So where are the original Minkowski spaces in the literature?
So I didn't draw the other half, which will be the below this picture, but this will be the Lorentzian picture.
But the half of each Minkowski space are the two top triangles?
Yeah, it's this one is a flat space, and these parts are in the gravitation. So I won't explain why it will be this particular form when you try to calculate things in the Euclidean signature. For example, you can find a metric in this gravitational region by taking the metric in Lorentzian and just analytically continue time to Euclidean. And then you will see that this will be a half thermal circle, similarly for flat space. But the main point is, once you have a representation for your state using path integral, then for example, you can see what will be the density matrix. So if this is the half of this is preparing your head, the other half is preparing your brow, and if you determine some field configuration on this side of the cut and some field configuration on the other side of the cut, that path integral will tell you what's the matrix element of your density matrix for this field configuration and this field configuration. But we are not really interested in the full density matrix. We are interested in the density matrix of region R. So what we have to do is we have to trace out the complement region. So once we prepare the stated path integral, we trace out over the complement, and tracing out means that you just, whatever you put on one side of the cut, you put the same thing on the other side of the cut. So basically that means that you glue the cut, so there won't be any cut in the complement region. So if you do this, whereas here you want to find the density matrix, so your boundary conditions, we are not specifying here. Depending on what boundary conditions for your fields you're going to put here, that will give you that particular matrix element for density matrix rho of R. So this is how we prepare the density matrix. And now that we know what density matrix is, we will try to calculate the entanglement entropy. And often when you have some representation for your density matrix, it's easier to calculate trace of rho R to the n for arbitrary integer n. And if you have that expression, then n will appear as a parameter. So you can hope that you analytically continue around n equals 1, which is known as replica trick, and you calculate the entropy using this formula. So you first calculate it for integers, then analytically continue, and then you take the derivatives and you treat n as a parameter. And this is called replica trick and not replica theorem, because it's not really proven this analytic continuation gave you the correct answers all the times. And there are counterexamples for the replica trick, but it's a well-justified assumption that we're going to use. So now, instead of calculating trace of rho to the n directly, let's first calculate something simpler. Let's try to calculate trace of rho R squared. So this is representing the rho. So rho R squared is you have to put 2 copies of this, and then because you are tracing, now you're gluing these 2 cuts on the both sheets. And if you calculate the path integral here, the idea is this is calculating for the trace of rho R squared. But not quite, because there is one important difference between these situations and the situation that there's no gravity at all. So remember, this region inside is a gravity, so there can be gravity and you have to solve Einstein's equations. The region outside is like field theory. So when we try to define the gravitational path integral, we can only impose the boundary conditions at the boundary. So we can't really say what will happen in the bulk. We just impose the boundary conditions for gravity, and then the gravity will feel the geometry with whatever way it has to feel the geometry. So we don't have control over how gravity will feel the geometry. We have only control on the boundary conditions. So when you try to calculate this trace of rho R squared, there is one obvious choice that, okay, whatever boundary conditions you have some boundary metric on ADS, you just fill this with a hyperbolic disk, or whatever it corresponds to the original geometry that we started with. And this path integral has nothing to do with the path integral on the other sheet. These are completely independent. They are just identified at these cuts when you try to calculate trace of rho R squared. So that's typically what we do, and we call this a Hawking saddle, because if you do this calculation and then analytically continue as a function of endpoints of this region R, you will find that the entropy increases forever. But the main conceptual point is there's actually another geometry, which we call it wormhole saddle, for the same boundary conditions you're imposing at the boundary of your gravitational region. There might be another geometry that actually connects these 2 sheets that went into the replica trip. mean, of course, this was trace of rho r squared. And the main idea is when you consider these type of geometries that are consistent with the boundary conditions, then the answer might be very different. And this is like a wormhole, because actually if you start from one of these sheets, you can jump into go to another sheet through this geometry, connected geometry. And once you're in this sheet, you can come back, since these 2 points are glued, you can come back to the first sheet. So like these curves are actually closed. So that's why we call them wormhole saddles. And whether or not what will appear, it's not really up to us. It's up to
How
how
is this
gravity.
more than just an identification?
Say it
You
again.
have, I mean, when you draw these like curved lines, you're implying something, right?
Yeah.
You're not filling it up with geometry.
No. It's basically just the boundary of this is the geometry. So it's a two-dimensional geometry. It's like a bridge, but at the end, it satisfies the same boundary condition on one sheet. It satisfies the other boundary
So
condition.
should I think I'm cutting a hole where those discs are, and then I'm going to identify the top boundary of the top disc with the boundary of the top?
No, we won't identify. It's just like you have some boundary, another boundary, and then you have.
I don't know what the intermediate geometry is. There's nothing between the two boundaries, right? I mean, the two stacks.
Right. So the idea is you can only specify the boundary conditions here for the gravitational region. And so in one sheet, you will say that, for example, at the boundary, the metric is something, and you say on the other sheet, the metric is also something, and then you just let the system, you have to just sum over all possible metrics and whatever.
I think this question is, it looks like you've turned a two-dimensional system into a three-dimensional system.
No, it's not three-dimensional. The geometry is not inside of this picture. So the geometry I was drawing there is just the surface of this. So it still is two-dimensional surface. Whereas in one case, your two-dimensional surface is just one disk and the other disk. So one case you have two disconnected disks. In another case you have the surface of this geometry which connects one sheet to the other.
Oh, so that shading is supposed to indicate that that's a hole.
Right, this shade is there because these are actually hyperbolic, so it's not like this distance is almost infinite, so it goes all the way to the boundary. So boundary is not a defined, like boundary is far, so that's supposed to be shaded, but yeah, it's just the surface of this.
And what you're just make sure I understand, you're saying that when you properly identify what you mean by trace rho r squared, the second option is what we must be doing.
So,
this
yeah,
is
so
an
I'm
option,
saying
right?
all of these in principle are there. For example, you can also have weird options that, you have this, like you can have even holes. Like you're trying to calculate this, but you also consider the one that has a hole. So all of these are in principle there, but if you try to do this path integral by saddle point, you have to just see what are your possible saddles. And one saddle that we always consider is their field independently, another one is disconnected geometry. And when you, for example, try to calculate this trace of rho r squared, well, there's one answer which is Hawking answer, this saddle point, and there's also this new saddle point that wasn't considered. And when you try to calculate this by saddle point, you should always choose the one that is dominant. So if S2 will be very large at late times, this will be very small compared to this contribution. And of course, there are other, like quantum corrections, all the other ones. So here I just wrote the saddle points that you have.
This is a quantum mechanical modification of the max over these two sets.
Yeah, exactly. That's the crude calculation we did, but yeah. So I could have said some of these also in Lorentzian, that in Lorentzian again, you wanted to calculate this region R, and for trace of rho r squared, we just dilute this region R. But whether or not the geometry that you have will be completely disconnected, or it will be connected by some surface like this, that's something that you need to solve equations, and it's not determined before you find saddle points. The idea is this saddle point will actually dominate.
I'm slightly uneasy because, I mean, the replica trick is a trick in order to, do a computation. I mean, presumably I could have done this, I should be able to do this computation in some other way and derive the same conclusion. Like, do you have an idea of what that would look like? That might be very many.
Basically, how do you find saddles if you don't do this?
Like, you don't do the replica. Like, I'm just curious, like, if I didn't know about the replica trick, could I have been smart enough to figure this out? To figure out that there's some funny configuration that in the replica trick picture looks like this.
That's, I think, an excellent question. I don't know the answer, but like, it's true that like, these saddles that I'm drawing here, they only exist when you go to these different sheets. So in the first sheet, okay, you might have just one this hyperbolic metric, and you might have all of these like funny higher genus surfaces, so in principle you have to sum over all of them, but it is a little bit puzzling that like you have to first go to the replica sheets and then you can see these saddles. So
like it's telling you that there's something somehow subtle about the quantum gravity path interval measure or something.
Well, it's something over non-perturbative configurations, and it's only giving you pictures.
Yeah,
of
okay.
Perturbative configuration. Sure. So something is,
yes.
Could you please say again why did you decide to kind of glue those two disks on the second picture, that surface?
Right, so the idea was when we try to deal with gravity, the only definition that we can have is like put some cuts, just like field theory, and put a boundary condition here. So that's how we can define it in a full quantum gravity, because we don't know what will happen inside this geometry. So the original point is we start with this, and here I haven't filled this, so it's just imposing the boundary conditions here. And then you will ask, okay, so now if you want to find the different saddle points in this geometry that gravity can fill in, what will be those geometries? And the idea is there are two different geometries that gravity will come and fill this completely independent of each other, and the other one is disconnected. But you should think that really trace of rho squared, when you try to calculate it, it's just meaningful when you haven't specified what you will get inside this geometry. So you have to just tell me what the boundary condition is, and then who knows what will happen. You have to sum over all possible geometries that can appear. Thank you. Yeah. So now that we saw how does it work for two of these, it's easy to generalize it for multiple, like for example for three, you have this kind of, again, connected pictures between different sheets. And this island point is nothing but the Zn fixed points of these replica manifolds. So everything here is smooth, but there's this Zn fixed point, these 2 points, that from the point of view of one of this sheet, it looks like this. So you have 2 points, it's like twist operator insertion that you're just enforcing the correct periodicity around them for your manifold. And you can either represent them like this, or you can always go to the covering manifold and you'll find things like this. So these points, like the end point of the island, is basically just like the twist operator insertion.
I think I know what that means in string theory, but what does it mean in geometry?
It just, for our purposes, it's just enforcing that you have to go, I don't know, for example, here you have to go 3 times around this singularity to come back. That's the only thing it does. But it is slightly different from the usual twist operators, because for these twist operators, everything is smooth. So for example, if you calculate curvature or anything, it will be smooth. Whereas for this type of twist operator we insert in like field theory, that's not typically smooth. Like the curvature will actually blows up at these points. But
So in a way, you're taking regions and sizing them, and then doing a sort of automorphism on the boundary and moving it back in or something like that.
Yeah.
And then you're gonna get some weird twisted thing that would not have been the obvious thing to, some obvious geometry to.
Yeah.
Yeah.
Right. So finally, the actual content, the theory that we solved this was 2D JT gravity plus some CFD. So formally, you can write down equations like the full partition function is sum over all metrics over all dilettante, because the gravity action depends on also on dilettante, times the partition function of your CFD, and the action for the gravity is this famous JT action, dilettante r plus 2 plus the equivalence Hawking term. And for this theory, now we have to just go and solve Einstein's equations for these pictures that I'm keep drawing. And what will happen is the Casimir energy of your conformal field theory will source this geometry. So there's a Einstein piece equals the matter piece. That matter piece is just coming from the CFD. Casimir energy, and we worked in a regime that's central charge of our CFD is much bigger than 1, and G Newton is also small. And the reason for that was we wanted to have a semi-classical geometry. So we wanted the stress tensor sources to be large, so it doesn't compete with quantum fluctuation. So we wanted to have a semi-classical space-time. So the matter contribution we had, we made it large by taking C to be large, but it doesn't have to be a holographic CFD. It can be just n free boson and just take n to be large. That will also do the job. So it doesn't have to be.
Repeat all the ingredients. So
Yeah.
M tilde M is what?
So
Is the
M
entire-
tilde was this covering
Yeah.
manifold, which is completely smooth. When you quotient it with Zn, I just called it Mn, which is this one. So you basically, over the full manifold that you construct, you have to calculate this action and vary it to
And then
find.
phi and phi naught and phi b are all what?
Right, that's a good question. I should have explained this. So phi is the dilettante in the bulk times r plus 2. Phi naught is just a constant in both cases, which if you think about 2D JT gravity coming from dimensional reductions of the 4-dimensional black holes, this phi naught has information about the original entropy of the black hole. So this phi naught is just a constant, and phi b is the value of this dilettante at the boundary that we specified. So this is part of this boundary conditions that I was talking about. The other part is just metric at the interface, what the metric is. So you start with this, and vary it with respect to G, vary it with respect to phi, get your equation, try to solve them for this geometry. Yes?
A very silly question.
Sure.
So the CFT is 1D, right?
CFD is 2-dimensional. So CFD was, so this wasn't holographic. So CFD was in this flat space region, but it was also in the gravitational region. So it was everywhere, and the fact that we chose CFD was just easier for computations. But it can be n free both, like of course n massless boson is also CFD, but it can be also massive. It just was easier to deal with CFD because you know that partition function is related to the partition function of the flat space. You're using anomalies and all those sort of convenience. So once you construct this wormhole saddles for general n, then again the trick is to just, when you have the equations, then you just treat n as a parameter and just take n near 1, and you'll find that the equation of motion itself will imply that near n equals 1, you will find something like n minus 1 times the derivative of matter contribution plus the derivative of this dilettante, which here dilettante is basically the area over 4G. And you will just find the equations that we were talking about, which you have to extremize the combination of the area plus matter, and that will just come out of equation of motion. So just some few last comments about this. So one thing is, when you go through this procedure of finding the island and where the island endpoints appear, depending on parameters, at early times, you might not find the island. It might be complex. And in general, the Hawking answer will be dominant at early times. However, at late times, always you have an island. There's always a solution for this. And the generalized entropy on this region R union I is always smaller than Hawking calculation. So we should choose that one. And it gives you this constant. And there's an easy way why there will be a constant, because if you go at late times, at very late times, the distance between these points will be very large, and the calculation for entanglement entropy will be basically dominated by some sort of OPE limit. Between you have two you have two twist points here, two twist points here. So at very late time, the answer for the matter will be basically given by some OPE limit, and that's the reason why you will get a constant answer. So it will be just some OPE limit between these 2 points and that 2 points, and it will be time independent. And finally, I should say that we chose C, as I said, to have a semi-classical geometry, but it seems that since the very late time argument is using OPE, this argument might be actually valid even if central charge is not large. Like if central charge is not large, you don't expect to find a good semi-classical geometry, so everything is fuzzy because of quantum fluctuations, but it seems that in very late times, because this argument relies on OPE, we might be able to still use this. But of course, it's a very important question, what is the role of quantum fluctuations, and for example, whether they break this DN symmetry that we considered for replica. Those are good questions we considered, but we didn't consider any quantum fluctuations for our geometry, just at the classical geometry. And just some future directions that I think are interesting. One is basically constructing these replica wormholes for evaporating black holes to get the old page curve that we wanted, that it goes all the way to 0. The other thing, so this is basically something that I'm working on. There's another interesting question that applying this island rule for other gravitational models. For example, the gravity models in flat space-time, in 2 dimension or higher dimension, and also the Sitter space-time, that it might have some islands, and I don't know what the explanation in that case would be, but this is, I think, something interesting. Another thing is, in usual ideas CFD, we have this entanglement wedge reconstruction to relate the operators in the bulk to operators on the boundary. So if this is really a true, if really the entanglement wedge of this island is contained in the region outside, there should be an explicit map between the operators in the island versus the operators in this region R. So you should be able to construct everything about this region island from the region R, and having an explicit map might be important for going toward this solving microscopic information paradox. And finally, I should say that this Euclidean wormhole also appears in the story of JT gravity equals ensemble average of theories in 2D. And the same Euclidean wormhole here appeared for getting a unitary phase curve. So it's interesting to see whether existence of this Euclidean wormhole tell us something about whether we should think about gravity as an ensemble average of theories, or it can be just dual to one particular theory. So these are some questions that I'm thinking about. And I have a few slides about basically this first point, but I think it's a good starting point, and I will answer questions.
So basically, we aim to preserve